So today's topic is microservices, and I think I mentioned this a little while ago. Kind of like I've actually been giving versions of this talk for 2.5 years now, and it was all about, and the big idea was decomposition, like breaking apps up into services. And then of course the term microservices came along, and I put microservices in the title, and just to be buzzword compliant. But the big idea is you break up the app into services, and it makes your app much more deployable, much more scalable, and in some ways easier to develop. And it also makes it a lot easier to embrace new technologies as they emerge. And I'm going to kind of, the whole talk's about that. So a little bit about me. So I actually got my start programming back in the 80s, doing Lisp systems. So I actually spent 7 years building various kinds of Lisp systems. Compilers, runtimes, frameworks, IDEs, garbage collectors, and all of that kind of stuff. I met Robert. Wasn't it you were doing Smalltalk back then?
Yes, I was.
Yeah. So that was a really long time ago. Yeah, there was like 86 to 93. And then, fast forward to 2005, 2006, I wrote a book, Pojos in Action, which was all about how to build apps with Spring and Hibernate, which back then were these radical new technologies that were, sort of transforming enterprise Java development. And, they're actually still pretty good. I still use the Spring framework today. And then back in 2006, this what's really interesting, I run the Java users group up in Oakland, and we had an evangelist from Google come talk about APIs, and they were talking about Google Checkout. And then this Amazon evangelist showed up, and I was thinking he was going to talk about APIs for building books, for buying books. And instead he talks about APIs for provisioning servers. And this like blew my mind. So much so that, I kind of signed up for the AWS program that was still like a kind of closed beta, and I started tinkering with it eventually. And that created an open source project around that, and that turned into my startup, Cloud Foundry, which was a path for deploying Java applications on Amazon EC2. And then that got acquired by SpringSource back in 2009, shortly before SpringSource was acquired by VMware. And I always like to make the joke that this was not drawn to scale in terms of market cap. Cloud Foundry was really a plankton. Not even necessarily that. It was tiny. It was like me, it was Robert, and another guy. And I actually had spent 4 years at VMware, which I then Pivotal, which I then left a year ago with the goal of figuring out what to do next. So I'm kind of pursuing some startup ideas and also doing consulting around NoSQL, cloud, AWS, microservices, and a whole bunch of trendy application topics. So that's me. So really the agenda is first kind of like look at the motivations for using microservices, dig into what it means, and then sort of explore various different aspects of the design of a microservices-based application. And then I added a little section on the end where I just kind of talk about some of the specific technologies that I'm using in my startup's app. And please feel free to ask questions at any point, because I think I've got enough slides for about an hour, but we've got like 90 minutes, so we can make this nicely interactive. So, let's imagine that you're building an online store, kind of sort of Amazon.com type application. And, if you're like me, a few years ago anyway, you would have probably built an application that looked like this. So, you'd have a presentation tier, storefront UI, and that would maybe serve up HTML. Of course, today it would expose a REST API to mobile devices. And then you'd have various back-end services like a service for product info, kind of the product catalog, a service for recommendations, a service for reviews, a service for dealing with order processing, and so on. So you'd sort of have this logically modular architecture, and it would use technologies like Spring and Hibernate and all that kind of good stuff. But then what you end up doing is actually packaging your nice logically modular architecture up inside a single WAR file that you then run on a server like Tomcat. And you just sort of have this, you have the application, just this monolith. So sort of who builds apps like that still? Anyone? Yeah. And if you're really lucky, you could have 1 million lines of code in there because you know, a team of developers busily adding code every day. Before long, you've got this massive application. But on the one hand, you know, this is not bad because apps like this are actually quite simple to develop, test, and deploy. In particular, you know, deploying your monolithic application just means copying the WAR file onto your Tomcat server and maybe restarting Tomcat. That's really, really simple. And you know, also it's pretty easy to scale, right? You run multiple copies of your application behind a load balancer, and you've got this app that can scale to handle increasing load. So that's really nice. And you know, the apps that I built, actually including the original version of Cloud Foundry, had this monolithic architecture. But the problem you run into, and maybe some of you are experiencing that, is that when your applications become large, this monolithic architecture really just causes a whole bunch of problems. Causes you a lot of pain. And with the original version of Cloud Foundry, we had pain as a result. Number one, you know, a large, you know, monolithic application tends to be pretty intimidating. You know, imagine being a new developer and you're given a task to make changes, and you've just got this massive system that you have to figure out, and where all the pieces are, and so on. It probably has quite a complex build system. So, you know, it's just scary. And, you know, once developers get scared, they don't make changes properly, the quality just deteriorates, and it's sort of a death spiral. A large monolithic application really isn't amenable to being redeployed frequently, because you actually have to redeploy the entire system, which can actually be kind of risky. You can actually have long-running background jobs, quartz jobs, that get interrupted when you take down the server and it leaves the system in an inconsistent state. I've had that happen. And also, because all of your eggs are effectively in one basket, there's a lot of fear associated with deploying a large monolithic application. So there's this fear of change, so you don't want to deploy frequently. And that just sort of, you know, you got long QA, and it just really slows down development, but especially compared with the state of the art, which is deploying changes into production many times a day. You can't really do that with a monolithic system. I think. Probably there is someone who's doing that. Another problem you have is that, you know, a large monolithic system can overload your IDE. You know, you suck a big code base, especially a Scala code base, into your IDE. It's going to run incredibly slowly, and which makes you less productive. It's also going to slow down your container, slow down your application server. You know, if you've got a large application, it can easily take many minutes to start up. And if that's part of your development cycle where you make a change, restart the server, try out, test the change, you know, you're going around this quite long cycle. And once again, you're quite unproductive because your application is large. And then also, sort of a large monolithic application is really an obstacle to scaling development. You really want to break up your engineering team into sub-teams where each team focuses on a specific functional area. And the problem you run into when you have a monolithic architecture is that in order to get changes into production, you might actually have to have a lot of communication and coordination between the various teams. So the UI team, you know, who are constantly changing things, and they just want to redeploy the new UI to do A/B testing, for example, can't do that because the back-end team has broken some piece of the system, and they haven't committed the fix yet, and so you can't push the latest version of the code into production. So it's kind of painful. And then I think a really big problem is that a large code base really ties you to the technology choices that you made at the start of the project. Because as you know, if you actually, you can't, you know, there's a lot of frameworks out there where you have to kind of embrace them 100%. You can't bolt them onto your legacy app without actually having to rewrite the entire code base, which is prohibitively expensive and risky, and you know, rarely works out successfully. And you know, I think this is one of the reasons why you find, you know, every so often I run into people who are still using EJB2 and Struts 1. Or it even gets worse than that. I mean, I've even heard of people who are using like some custom macro assembler language from the 60s because they got some mission critical system that they just can't rewrite, you know. So anyway, so I think, you know, that's a key problem with the monolithic architecture. It doesn't let you freely try out new languages and new frameworks that easily. And that, I think, you know, leads to the sort of zombie-like state of many applications. Especially today, because things are new stuff, some of it good, some of it not, is coming out all of the time, and it's just good to try it out. All right, so those are the problems with the monolithic architecture. Even though it's, interestingly, it's actually simple in some ways, but it doesn't really scale to deal with complex applications. Later on, I'll tell you why microservices are a bad idea as well. But, you know, there's no silver bullet, right? So anyway, a few years ago, I read this book, The Art of Scalability, which was written by some guys who had worked at, eBay and PayPal. So it wasn't actually that technical a book. It was really about scaling architecture, scaling your engineering organizations. They later came out with a more technical book, the like 50 Rules of Scalability. But this book was fascinating, and one reason it was so interesting is that they had this three-dimensional model of scalability, the scale cube. And so there's three axes, three different ways of scaling your application. And so one of them was the x-axis scaling, which is just a horizontal duplication where you just run multiple copies of your app behind a load balancer. So that's sort of the standard thing that we've been doing for years. Then there's also z-axis scaling or data partitioning, where you use, say, at the database level, the value of a column to determine which server that particular row should reside on, so that's sharding. But you can also do that at the application level. You use an attribute of the request to route that request to the server that can handle it. Maybe you route free customers to one set of slow servers and paying customers to the much faster servers. So this sort of x-axis thing kind of works at both levels. And then what's really interesting is there's y-axis scaling or functional decomposition. And that's kind of different, whereas x-axis and z-axis scaling are about running different copies or the same copy of the application multiple times. Y-axis scaling is actually splitting up your application into things that are different. So it's sort of functional decomposition. And really that's kind of the essence of the whole microservices thing, or the service-oriented architecture, is that it's about functionally decomposing your system into a set of services. So if we apply that to this online store, we end up going from this to a system that looks like that, where each of what were logical modules of your system are now actually separate physical running services that can be independently deployed and scaled. So if we want, we could apply, we can also split up the front end as well. So instead of a monolithic UI, we now have a modular UI where, you know, different mini web apps handle different parts of the UI. And then we can apply x-axis and z-axis scaling to that, so sharding where it's appropriate. You know, most services we want to run multiple copies of for availability and scalability and so on. So that, you know, that in essence is the big idea. And then what are these services? So there's a whole bunch of different deployment options. So if you take Netflix, for example, you know, each kind of service is an AMI that gets, and then they run multiple EC2 instances based on that API, based on that AMI. So it's really a service per VM, or it could even be a physical machine if you're running in your own data center. Now, of course, Docker is one of the latest hot things, right? And it just so happens that Docker is a really great way of deploying microservices, especially because lots of Amazon EC2 instances are quite can actually be quite expensive, especially because, you know, these services might actually be small and they're not fully leveraging a whole EC2 instance. Whereas with Docker, you can have lots of containers running on fewer EC2 instances, so that's quite appealing. And then there are other deployment options, like there was some kind of like Google-like internet company in China where, because they were operating at such a huge scale, they actually deployed each microservice as a OSGI bundle. So that was actually an interesting use of OSGI. So in one JVM, they actually have many small microservices running, which means basically you've got, you know, it's kind of the most densely packed way of deploying microservices, though there's a trade-off with manageability and sort of isolation and visibility into resource utilization and so on. So there's a bunch of different ways that you can deploy these services. But I definitely like the first two, as an EC2 instance or as a Docker container. Okay, and then there are partitioning strategies, like how do you break up the system into services? So one way of doing it is partitioning by noun, and so you could have a service that's responsible for anything to do with an entity of a particular type. So a customer management service or a product info service, or an order service. Or you could partition by verb, where it's sort of there's some service is responsible for a particular use case, a particular action, like checkout, for example. And then there's a few guidelines. There's like the single responsibility principle from object-oriented design that says a class should only ever have one reason for change. It should only ever have one responsibility. And you could apply that concept, that kind of thinking, to service design as well. So a service just has one responsibility. So small, cohesive service. Or you could kind of emulate Unix. So if you think about Unix, right, at least with the command line, you've got all these tiny little utilities, cat, grep, find, maybe some are not so small like or. Actually, I wrote some more scripts the other day. But each one of them's kind of got a small, focused responsibility, but you can combine them together in shell scripts to accomplish, much larger things. So that's kind of a nice sort of paradigm for thinking about microservices. And there's sort of like, you don't want to have too few, because you end up with, instead of one big monolith, you end up with a few medium-sized monoliths, so you haven't exactly solved the problem. And then there are people who argue that you shouldn't, you can have too many. This so-called, from SOA, there's the nano-service anti-pattern. And that's, that's a risk as well. Obviously because there's various downsides with having tiny, tiny services. It can be inefficient because of the runtime overhead of each service. If each service is an EC2 instance, that's a heck of a lot of overhead, right? Just for running 10 lines of code. you know, a real potential problem is too many network hops. You don't want to have a request come in and then bounce between a whole bunch of servers before going back out again, because that will give you a terrible response time. Though interestingly, if a request comes in and you invoke 100 different services in parallel, that will still give you kind of a good response time. So it's really the style of communication rather than the number of services that are involved that determine whether it's good or bad. But then there is this problem that, whereas before we have one thing that's complicated, if you then kind of have lots of services, you have lots of small things that are individually quite simple to understand, but now you've moved the complexity into the space between the services, and figuring out what the heck is going on in your system can actually be quite difficult. So there's a whole bunch of trade-offs, and I'm kind of, you know, doing some hand waving here. So that says it's something of an art, and I think it kind of is. So, you know, so what does a service look like? Well, here's one. This was kind of cool. So one of the Spring framework has been awesome for many, many years, and nothing that new has come out, except recently, I think it was a year ago, Spring Boot came out, and I'm going to talk a little bit about that. And this is a Spring Boot application in a tweet, and it's a hello world. It's a RESTful hello world microservice. So yeah, in theory, you could have tweet-sized services, but probably not. Though one of my demo apps I wrote, it was actually, it was a service that was written in Sinatra, a Ruby web DSL. And it was kind of like 10 lines of code, and it auto-responded to incoming SMS messages by telling the user to go to a registration URL. And to me, that was actually a legitimate service, right? It was only 10 lines, but I deployed it, never touched it, and the rest of the system was changing around it, and I thought that was fine. But you know, the reality is that I think one of the problems, like, you know, I mentioned this before we got started, I think one of the problems with the term microservice is that it kind of emphasizes small, kind of too much. You know, whereas service-oriented architecture, that's sort of a neutral thing, right? You break it up into services. Now, you know, so I kind of think, you know, think about services and not so much about the micro bit, and work on kind of decomposing your system into meaningful services that kind of solve the problems with deployment and scalability that you're actually embracing, rather than aiming to have lots of 100-line services. So yeah, so less micro, more service. So I think if you look out in, you know, the real world, or at least the web world, there's lots of examples of this architecture being deployed. And interestingly, each of these companies, Netflix, Amazon, eBay, they all actually had a monolithic architecture at some point during the life of the company. And then at some point it became too much trouble, and they went through the process of refactoring or rewriting and creating what they would now call, you know, in some cases like 15 years later after they did it, a microservices architecture. So, you know, so Netflix, you know, they're kind of the hot tech company right now in terms of thought leadership. You know, they've talked about having 600 different types of services in their system. Interestingly, if you do the math, right, I mean, you know, those are not 100-line services, because I think they have more than 60,000 lines of code in their system, right? You know, they're reasonable size. And Amazon, you know, they have a service-oriented architecture as well. And, you know, obviously they don't disclose too much about the details, but, you know, the high scalability website talks about, you know, hundreds of services getting invoked in order to supply all the pieces of data that go on a web page. So if you actually go look at the product details page, right, there's a ton of information on that. There's the basic information about the product. right? So you can imagine there's a product info service, but then there's reviews and recommendations, so there's two services. It actually will tell you when you last bought that product. That's another one. It actually tells you when you can get it, so it sort of kind of knows about shipping type stuff. There's seller rankings. And if you keep scrolling down, there's just like more and more pieces of data. So you could imagine the front end that's assembling that page is actually sort of, broadcast to a whole bunch of services. Tell me what you know about this product, and then assembled that data and rendered the HTML page. It's real interesting. And then of course eBay, who back in the day were the hot thought leader in the tech world. They said back in really long time ago, back in 2006, kind of had some interesting talks on architecture. One of which was actually at SD Forum, the predecessor of SV Forum. So it's kind of very much real world stuff. I don't know if there are big companies out there with massive monolithic architectures. Maybe not so much newer internet ones. Though I did once talk to a financial services company, and I think they had a whopper of an application. Millions of lines of code just packaged up as a monolith, and it must have hurt.
Well, how prevalent is it, do you think, that there's like big organizations that kind of every group wants to do their own thing and reinvent their own wheel? They don't communicate a lot within each other. Is that a problem? I mean, so it's kind of like a microservices, but yet they're not interacting with each other.
Given the dysfunction that's common in large companies, it probably happens.
Okay.
I don't know, but just speculating, I'm sure it does. I mean, it's almost like anything you can imagine bad about software development is being done.
So if you want to be an agent of change and you want to start, integrating those applications within that company, how do you? Maybe it's a different topic, but how would you kind of then try to bridge those different? I mean, with this approach would be the way to bridge it, right? Then, or
well, that's interesting because I kind of I think about ESBs, right, enterprise service buses, and they were the way of tying together all of these sort of different applications. I guess I think about, if you think, to me, the kind of the change scenario is you work at a company that has a large monolithic application, and it hurts to do development on it. So then the question is, how do we incrementally decompose that monolith into a set of services? I think that's kind of the more relevant question here. So I think if you've sort of got these, bunch of services or apps, and they must be talking somehow, you've got a sort of service-oriented architecture, just not a very good one, perhaps.
Not a lot of automation, more Excel spreadsheets.
Oh, yeah.
Yeah.
Interesting. Ping me, though. So, there are a whole bunch of benefits with this approach, right? Number one is, instead of a big monolith, you've got lots of relatively small services, each one of which is easy to understand and easy to develop. So that's definitely good. Less jar class path hell, which you can run into with very large applications. And I think that, say, one of the motivations for using for OSGI was really to solve the problem of I've got this giant monolithic application. How do I redeploy different bits of it? How do I deal with class path complexity and so on? And so if you've actually broken your app up into lots of little services, you've eliminated the need for OSGI. Which, at least from my perspective, is really, it kind of reared its ugly head back in 2008 as a developer conferences, and hasn't really been seen since. So I don't see it as that kind of big a big a deal anymore. Though apparently, yeah, there was some, yeah, I guess it's still evolving. Saw an announcement about it. And these apps tend to be faster and simpler to deploy. You know, I use Scala for development, and I really like Scala, but the Scala compiler is really slow. And the nice thing about a microservices architecture is your apps aren't that big anymore, and so the compilation time is much more manageable. And then they're just kind of tiny to move around and push into production as well, so it's just faster. And then interestingly, I mean, at one point, I don't know how relevant this is anymore, but on Google App Engine, your app had to sort of respond to a request within, you know, was it like 30 seconds or something like that? And some web apps don't actually start up that fast because they have lots and lots of initialization to do, and so Google App Engine would just decide that your app is not functioning and kill it. And so, you know, this kind of microservice architecture addresses that problem as well. And then it lets you scale development, right? Like you've got, you know, each team can work on one or more services, and they can develop and deploy and scale their services independently of what all of the other teams are doing. So provided you're not working on features that span multiple sort of teams, then there's no, which a lot of changes don't. They're just sort of within a service. Then this is really, really good. You know, teams aren't having to coordinate and communicate all of the time in order to get their changes into production. They can each work as fast as they need to most of the time. And then this approach also improves fault isolation as well. You know, whereas in a monolith, one misbehaving module that sucked up all the CPU or had a memory leak could bring down the entire monolith. At least in this architecture, it's only going to impact a given instance of a given service, and the rest of the application is going to keep working. So that's quite nice. And then I think a huge reason for using microservices is that it really gets rid of any long-term commitment to any particular technology stack. Because you've now got lots of little apps, and in each one could kind of use whatever framework, whatever language seems fit, right? You know, whatever technology is best suited for solving the problems of that particular service, whatever technology is new, hot, and fashionable, you can just start using it, which is kind of good. You're no longer stuck with Strut1, EJB2. Or whatever legacy technology you picked 6 years ago. So you can kind of think of your system as having two different levels of architecture. So you've got the system level that's saying, well, we've got these services, and each service has this interface, and they communicate using these mechanisms. And that can be the slow changing architecture, perhaps determined by people who use PowerPoint and never write code. But then the individual services kind of have their own architecture, and within reason, the developers of a given service are actually free to use whatever technology they want, provided they implement the official interface. So, and of course, you know, if you've got a REST interface, there's a whole bunch of different technologies that you could use to implement that RESTful API. You can pick the best tool for the job, but also, because each service is small, you know, there's nothing to stop you rewriting a service to try out a new technology. Imagine you know, if you've got a million-line app, you're not going to rewrite that because you want to use the Play framework instead of the Spring framework. You know, it's just not feasible. Whereas if you've got, say, a 3,000-line application, if you want to rewrite it using in Play, just to see how it goes, you know, that's not going to take you too long, and if it doesn't work out, you know, you haven't wasted that much time. Whereas if it works and you find that play is better than Spring, then you've learned something valuable that you can then apply to other services. And then also, you know, when you start a new service from scratch, at that point in time, you can sort of think, well, what technologies should I use? Which is a different, you know, which will have a different answer to that question than would have had like 5 years ago, for example. And there's all this, you know, you look around today, there's all this really cool stuff out there, some of which is quite good, right? You know, different languages like Clojure. If you're feeling crazy, you can use server-side JavaScript. You know, there's old-fashioned things like Python. And then, you know, then the Scala world, there's a whole bunch of, you know, Akka is pretty good, Play is interesting. I'm a big fan of Spring Boot. I think it's a great technology for building microservices, but then there's also other options like Dropwizard. And last night, Jason Schwartz from Netflix talked about how they've been using Scalatra, which is a Scala-based web DSL that sort of was inspired by Sinatra, the Ruby-based web DSL. And you can write tiny little programs in these DSLs that accomplish powerful things. So it's sort of, you know, a lot of productivity. But then also, as I said, if it doesn't work, if you're free to experiment, and if it doesn't work, you've learned something. If it does, you've also learned something. And I think this is one of the big benefits of microservices, is you can try new stuff out safely. But having said all of that, you know, there's a bunch of drawbacks. I think a big one is complexity. To the point that sometimes it can hurt, you know, because now you're developing a distributed system. So whereas before it was a monolithic application, and when service A called service B, that was just a regular method call. It was nice and simple. But now in order for A to call B, it's an RPC call. That's a lot more complicated. You have to program to deal with, well, you know, number one, speed of light suddenly is important. Network latency is important. Then you also have to program to deal with partial failure as well. So A can call B, but B might not be up, or it might be slow, and you have to program around that. And so you just got all of this complexity of distributed systems development that you didn't actually have to deal with. Oh yeah, and you also had to figure out where B is, right? Because you've got to do some kind of service discovery. And, you know, so you've gone from writing simple Java code or simple Ruby code to distributed systems programming. And that's kind of painful. And then also sort of worthy of special mention is the fact that, you know, if we decompose the system, then we sort of decompose the databases, and now we have to deal with, you know, implementing transactions that span multiple databases without actually using two-phase commit. And that's kind of painful as well. Pain. There's lots of pain. Testing is painful, or can be. Whereas before, if we wanted to test the application, we just spun up our WAR file, made sure it was talking to a database. But now when we want to test our service, there's a whole bunch of services that it depends on. And they have to be launched as well. So that's complexity. I mean, you know, in a way, the nice thing is many of these problems are solvable with the right level of automation. So it's not like they're sort of unsolvable problems. And then also we're now deploying this distributed system. We can't just copy a WAR file onto our Tomcat server. We've got lots of moving pieces that have to be rolled out. And then actually diagnosing faults is challenging because the request might have touched multiple services, and any one of which could have failed, and actually sort of diagnosing the root cause can be quite time consuming, especially if different services are owned by different teams and you actually have to communicate, and fault resolution can take a while as the trouble ticket gets bounced around. And also, whereas deploying changes within an individual service is incredibly easy, deploying changes that span multiple services requires a lot of careful coordination and sort of to actually, you have to start at the bottom of the dependency tree and roll out the updates and move up. So that's kind of complicated. Yeah, automation, once again. And then the other question is, well, when should I use that? You know, if I'm working on a startup, I don't have any issues of scale. I don't have any issues of code complexity, so should I really be using a microservice architecture to solve problems that I don't have yet? But then the problem you can run into is later on when you do have those problems, actually kind of refactoring into a service-oriented architecture, remodularizing your code can be kind of tricky and painful. So obviously people have done it, but it's not necessarily straightforward. So there's a lot of, you know, so on the one hand it's a really cool technical approach, but then there's some real complexity and pain associated with using it. All right, so that's kind of, any questions, by the way? Yeah.
So I see a lot of articles and on automation on the service side of things, but they just magically assume the UI can consume those services. And is there like a standard framework for on the UI that can consume this multiple services? And
ask me that question at the end of this section, because it kind of touches on that. Yeah.
I was intrigued by your when to use it question, because I think that's something working in an enterprise IT shop, that's the question we often face, because a lot of things that the born-on-the-web companies do, they are really architected for the web scale. But if you're developing something for the enterprise users, which you probably number in hundreds or thousands or tens of thousands, but certainly not in the millions or
yeah, I mean, you're sort of touching on a sort of real problem with thought leadership within software development. It's mostly led by consumer-oriented internet companies, the Facebooks, the Twitters, the Netflixes, who have to do things on a scale that most people don't. So yeah, I mean, you know, it's kind of like, you can get a lot of mileage out of a monolithic application talking to a relational database, you know, using SSD drives versus a microservices application talking to a NoSQL database, right? It's just, you don't, I mean, you don't necessarily have the massive scalability problems. Yeah?
So sometimes when we split the monolith, there are areas that are actually common to most services. An example is authorization and authentication. How do you actually decide whether that becomes a service or it becomes a library? I see like sometimes you have to make a decision between whether it's a library that's statically linked versus a service that comes with a cost. How do you make that decision?
Yeah, that's sort of interesting. I mean, I don't have a precise answer to that, but I mean, so definitely you need to have libraries that are shared between different services, which is straightforward if those services are written in the same language, whereas if one's Java and the other one's JavaScript, you have a real problem. And yeah, and then other things, you know, if you've got some service like, I mean, I think of authentication and it's maintaining data and state outside its own data and state, then it needs to be centralized and its own service and not embedded elsewhere. So yeah, I mean, it kind of all depends. Alrighty, let's move on. So now I kind of want to talk about the problem where I've broken up my app into all of these services and how do these services communicate with one another, and then also how to clients of those services communicate with them. So kind of a couple of different related areas. So, you know, so this is the Amazon product details page, right? I think my book is actually, you can still buy a copy of my book there, though. Don't know why. But, you know, as I mentioned earlier, you look at Amazon's details page, there's all this information that you could imagine being pulled out of different services. So in the case of, you know, this simple online store, it's got product info, reviews, and recommendations, and each one of those pieces of information about a product is stored in a different service. So you've got some client of those services, which could be a server-side web application that spits out HTML, or it could be a mobile client, native client, or some app that's running inside the browser on a device. And they need to talk to those services to display the product details. So one option, of course, is that they could just access those services directly. You know, it's not, even though there could be hundreds of them, I guess they could be accessed over the internet. Except that that's a really chatty API. You know, there could be 50 calls just to get the information to display on one page. Not so bad on a LAN, but over a mobile network, that would seriously suck. And then maybe some of those services have protocols that aren't web-friendly. They don't want to go through firewalls and that kind of thing. So the solution there is rather than having clients talk directly to the back-end services, instead what you do is put in the middle an API gateway, kind of like a front-end server that clients talk to, and then it talks to the back-end services. And that acts as a single entry point, and then provides APIs that could actually be specific to each client, and they would be web-friendly, or in some cases, so it can do things like protocol translation. So that for whatever reason, the review service has an AMQP messaging interface. Don't know why it would, but that doesn't go over the web, but the API gateway translates it into something that is web-friendly. And then, you know, a really interesting thing that this API gateway can do is provide APIs that are specific to a given client. So if you've got some front-end web application that's accessing the application over a LAN, high-speed, low-latency network, then it can just it can speak a chatty, fine-grained API, because that's just fine. Whereas if you've got some mobile app that's accessing the service over a mobile network, over the internet, in order for that to be efficient, you need to have a coarse-grained API. So the mobile app would just request the product details, and then the API gateway would call all of the relevant back-end services and gather up the product details and return them in one go. So just one round trip. And that's kind of really hugely important with dealing with mobile devices. And even there's an argument to be made that the web application, even though it's going over a LAN, maybe you should encapsulate the different partitioning of the services behind the API gateway, and so it just asks for product details and doesn't actually know which services are involved. So this kind of, you know, plays a role of encapsulation as well. And Netflix have written quite a bit about that. You know, they talk about, you know, they're supporting a gazillion different kinds of devices, and their API gateway has device-specific APIs that just make life easier and more efficient for the client. And then it cools out to the underlying back-end services. So a whole bunch of challenges with building an API gateway, particularly at scale. So, you know, you want to have like asynchronous event-driven I/O. There's also a challenge with dealing with partial failures because, you know, maybe the recommendation service is down yet again. And so, you know, you kind of have to recover from that and return the product details minus the recommendations so the page can just sort of mostly be rendered. So there's stuff you got to handle around that. And there's a whole bunch of technologies that you can use for building high-performance gateways. So on, on the JVM, there's Netty-based frameworks like Vertex or just Netty itself. Netflix have Hystrix for cooling, doing remote cools in a fault-tolerant way. And then in the system, I actually hacked together my API gateway using Node. Even though I hate JavaScript, but it just kind of is it's sort of well suited for simple things like the gateway. Okay, so then the other thing is, well, if we've split up the web front end, we've got lots of little web applications. How does the browser interact with all these different little web applications? And it's kind of the same sort of problem with the same solution, as you kind of put like a API gateway, or so to speak, between the browser and the various web apps that just does routing based on the URL to the appropriate web application. So that's sort of another little piece. So the browser doesn't really know how your web application has been partitioned. Yeah?
So for the gateway, doesn't that add an extra coupling to your system? So every time you change an API in your service, now you also have to change your API gateway? Usually you would like to avoid that coupling in such a system.
Well, that's interesting. So a back-end service could actually, as part of it, the service discovery mechanism, could just say, I'm available and I support these URLs within the overall URL sort of namespace. So then when a request comes in, the API gateway can use the service discovery mechanism to figure out which back-end service to route that request to without it being hardwired into the gateway. I mean, like right now with my app, it's really simple. So my gateway just says, /foo goes to this server, to this Docker-based service running on this port, /bar goes to that one, but ultimately there will be some fancy discovery mechanism so that it's all of the routing is data-driven.
Is the discovery being done all the time, or just certain times? This comes up.
Yeah, I mean, you can poll. I mean, there's poll. I haven't figured out the details, but I mean, there's various sort of options, right? You cache the discovery, so you're not doing it on every request. That would make sense. Could be event-driven in some way. Cache invalidation based on events. Bunch of different options there. Yeah.
So, how do you think about the existing API management tool like Mashali or AWS?
I haven't really looked at them. If I were to guess, I would imagine they're kind of heavyweight. In the sense that, like, my API gateway, it's actually doing a bunch of things, including OAuth authentication, but the actual routing is like 10 lines of JavaScript code. Yeah. So it's not a big complex task. But of course, it's not doing kind of metrics or any, I mean, there's sort of, you could do something more elaborate, I guess. Alrighty, so then the other part of this is, well, how do these services communicate? And there's a whole bunch of different options, right? So you have a synchronous protocol like HTTP, a messaging-based protocol. Then there's a whole bunch of different message formats, right? JSON, XML, protocol buffers, thrift format. And so there's a ton of different choices. You could say that kind of asynchronous is sort of preferred because it's got some benefits, but REST is hugely popular. And of course, JSON is really, really popular these days. But a binary protocol is actually more efficient because you don't actually have to parse it. So there's a bunch of different ways, and people are doing it, picking some combination. Messaging is quite nice because you don't actually have to do any discovery. You just talk to the message broker and say, send a message saying do this, and then the back end, it gets routed to a back end service, which the client doesn't know about, and if the back end service is down or unavailable or slow, the messaging broker buffers it up. So that's kind of nice. But if you just want to do a request reply style pattern of communication, doing that over messaging is a little sort of a roundabout way of doing it. So, HTTP or Thrift is another option, and that's sort of, simple request reply, straightforward, firewall friendly, which is good because you might be communicating with a native client. But then in some cases, you'd actually have, you have to know where the server is that you want to talk to. And, in this sort of microservices world, and in the cloudy world, you need a service discovery mechanism in order to make that work, right? And that could be, one option, of course, is like using a load balancer. So the services register with a load balancer, the client talks to the load balancer that's on some well-known URL, and the load balancer routes to the appropriate instance. And so, if you were using Amazon in a VPC, you could create an internal, non-publicly accessible load balancer to manage this. So that's another, and then another option, which is, say, what Netflix have done. It's basically client-side service discovery. So the services register with a registry. In Netflix's case, it's Eureka, but other people use Zookeeper. And then the client asks the registry, where is the service, where are the instances of the service? And the registry says what the hosts and port numbers are. So that's another option that's sort of, this is quite popular, I guess. So this kind of the upshot is, there's all these moving parts. We've gone from like simple monolithic system with a load balancer to like lots of services, API gateways, content routers, some kind of service registry to do discovery and so on. So it's all a bit complicated, but generally kind of worthwhile. All right, so kind of in the final part of the talk, kind of want to talk about decentralized data management, which actually sounds really boring and bland, but it kind of has a really big impact on actually the whole system architecture. And kind of the big motivation here is, well, if we've decomposed the services, we've decomposed the database as well. In order for these services to be loosely coupled, really each service should have its own database. And so, the order management service, which keeps track of orders, will have an order database. Customer management system will have a customer database. Means that they can evolve quite independently of one another. And you could imagine kind of having an architecture where one service might use a relational database, where another service might use Mongo. Because, Mongo is web scale and all that. Another one could use Cassandra, another one could use Neo4j. So kind of got this whole polyglot persistence architecture. And it sounds great, except that, you think about your database schema, it's actually really hard just to slice it up into independent things because an order actually has a foreign key back to the customer, right? And customer OO terms, there's sort of a bidirectional relationship between the two. And so, in my example, I've got an order has a total, and a customer has a credit limit. And then there's a couple of invariants that need to be maintained during this at all times. So number one, the sum of the open orders must not exceed the customer's credit limit. So that means that in the order service, in order to place an order, you actually need information, you need the customer's credit limit in order to do that. And then likewise, a customer has a derived attribute, the available limit, that's the credit limit minus the sum of the open orders. And so in order to compute the available credit, you need to know what the available orders are in the order management system. So kind of when we split it up, there's this nasty relationship between the two that kind of gets in the way. And this is kind of the nature of the system, is that partitioning kind of doesn't exactly work at the database level, and So there's a bunch of problems you have to solve. So specifically, you know, service A, in order to handle a request, needs to read data from service B, or you have to implement a transaction that actually updates data that's owned by multiple services. And that's a particularly hard problem to solve because, you know, two-phase commit is sort of proper distributed transactions are not fashionable anymore. So there's sort of a bunch of challenges. So, you know, how can you handle reads? So one option is when you place the order, or when the order management system is processing an order, it can just go get the credit limit from the customer and do the check. So there's sort of the pull approach, right? And on the one hand, that's simple to implement, ensures you've got up-to-date data, but now the order service is dependent on the customer service being up. So we kind of introduced this coupling, which increases latency and also can impact availability as well. So maybe that's not a good idea. The other option, of course, is the customer service can actually replicate the credit limit to the order management service. So the order management service no longer has to go out to the customer service in order to get it. So, you know, that seems weird because we all know that we're meant to use sort of normalized data, right? We shouldn't have these copies of data just sitting around. But, you know, one kind of sort of conceptual justification for this is in the book Domain-Driven Design by Eric Evans, there's a concept of a bounded context, which sort of says that, well, in one part of your system, you might have this thing called a customer, but that part of that sort of module's view of a customer could actually be wildly different from another view of a customer. So like, I don't know, order delivery is concerned about customers and their addresses, whereas kind of another part of the system might just be concerned with like customer care and how many times they've interacted with the company. You know, so marketing's view is different from the shipping system's view and so on. And so it's actually okay for different parts of your system to have different domain models where there's like a customer prime in one module and a customer double prime in another one, and they have the customer ID in common, but everything else is kind of different. So this kind of notion of replicating data is not such a bad idea, right? It kind of improves availability. It means that a service has the data it needs without having to call out to other services. But then the question is, okay, so how do we if we've got credit limits scattered throughout the system, how do we keep them synchronized? So it's sort of problem upon problem here. And so one option, of course, which is sort of a non-starter, is to use a distributed transaction. So when the customer management service changes its credit limit, it actually starts a distributed transaction that updates the order management service. And while that has kind of, from a developer's perspective, a nice simple programming model, from an operational perspective, using distributed transactions, you know, is complex, it impacts availability and so on. And for the most part, people don't use, you know, at scale, people don't build systems this way. And so that then leads to using an event-driven approach where a service like the customer management service will just publish an event. The customer's credit limit has changed, and then the order management service will subscribe to that event and update its copy. So you've sort of got this eventual consistency model, which kind of is operationally simpler. It's a little more complicated from a developer's perspective, but it means that our systems are sort of nicely, loosely coupled. But then you've got the complexity of actually having to deal with eventual consistency, where, you know, you've got some transaction in progress and the changes haven't been fully replicated, and then you go and look at the data and it's actually inconsistent, and it's like, things just aren't quite right, and you have to like try again in 50 milliseconds when hopefully those changes have propagated. So that's the sort of more complex programming model. And then whenever you're processing events, there's always the possibility of having duplicate events, which can sometimes be tricky to deal with. Like actually doing duplicate detection can be hard in some situations. So there's all this complexity around that. Though I think, to be fair, kind of this event-driven approach is kind of quite common. So then that sort of leads us to another question, sort of like the fourth question in a row, which is how do systems deal with it? How do systems publish an event? And sort of the challenge is that you actually need to publish an event whenever the application state changes. But you have to do that atomically, right? Because you update the database, commit the database transaction, and then try and publish the event. Well, maybe between the commit and the publish, your server crashes, and you never publish the event, which means downstream the consumers will be out of date, which is sort of bad. And if you try and do it in any other order, there's a scenario where the database transaction doesn't actually gets rolled back, but you've published the event, and it's kind of tricky without using two-phase commit. So there's sort of two problems, like how do you generate events? How do you detect that things change? So you could do it at the database level. You could have a database trigger on the customer table that, quote, publishes an event whenever an update is executed against the customer table. I built a prototype where I was plugging into the ORM layer to do that. You could mix event publishing code into your business logic to say, hey, this has changed, published an event. So that's kind of messy. And then there's a couple of sort of domain-based approaches where you actually take an event-centric approach to designing your business logic so that events just naturally get processed. And I'll talk a little bit about that in a minute, particularly event sourcing, which is something I'm really interested in. And then the other part of it is, well, we've got an event and we need to publish it and update the database. And then it's like, well, how do we do that without using two-phase commit, which is sort of the thing that we're trying to avoid. And especially modern message brokers often don't support two-phase commit anyway. So, if you go back and look at eBay, which wrote about this 2009, I think, they actually used a two-step approach where the message store, kind of a quote, message broker, was implemented by using a database table in the same database that the business data was stored in, which meant that you could update the business data and publish an event by inserting it into an event table within the same local transaction. So you had a nice local ACID guarantee at that point that either both of them had happened or neither of them had happened. And then there was a separate process that was polling the event table and applying those changes sort of downstream atomically. And that sort of worked out really well. And that actually works really, really well in a SQL database, but not so much in a NoSQL database. But this two-step, eventually consistent approach is quite good. But what I've been interested in is this approach called event sourcing. And the big idea here is that you actually write your business logic in a totally event-centric way. So what's interesting, so a request comes in, HTTP request, you construct a command object like debit the account or change the credit limit, and then that gets sent to the customer aggregate. And the way the aggregate responds to a command is by generating, well, 0 or more events. So that processing the command doesn't change the state, it just gives you events back. And then you apply those events to the aggregate to update its state. So that's sort of the model. And then the other critical part of this is that you never persist the current state of the aggregate or entity. You actually persist the events. So, and if you want the current state, you just replay the events. So you kind of create a blank customer and then replay all of the events that capture all of the changes that have happened to that customer since the beginning of time to reconstitute the current state. So everything is event, so even your persistence mechanism is actually event-based. It's kind of like you've got an event store that's a combination of a database plus a message broker all at the same time. So graphically it looks like this. A request comes in, you want to update a particular entity, you go find its event, and then these slides are written in terms of an account, and then you apply the events to the account, or it could be customer, to reconstitute its current state. You process the command, which gives you some new events, and then you persist those events, which actually just get appended onto the events for that particular entity. And then what's really cool is on the other side, you can have another service that's subscribing to those events, and they get published by the event store, and then that event subscriber could then go and update some other entity that could be used to kind of update the copy of the customer in the order management service, or it could be used to update some other SQL database or text search engine that's providing a different view of the data. So when you're using this approach, it kind of looks like this. You got the customer management service publishes the customer credit limit updated event, which the order management service subscribes to so that it can update its version of the customer. So you kind of got this model where all these services are just like publishing events as things changed inside of them, and other services are listening to those events, processing them, which can generate more events. So events, just sort of everywhere. And it's, you know, it's thoroughly event-centric. So like, this is what one of my domain objects looks like. So it's got two methods: process a command that maps a command into a sequence of events, and then apply an event that actually, this is an immutable domain model. So applying an event creates a copy of the entity which has been updated, so that you never update an entity in place. And then the underlying event store basically has methods like save new entity with the ID and a list of events, update an entity with some newer events, and then loading an entity just gives you back a bunch of events which it then applies to reconstruct an existing entity. So it's all very, very event-centric. And it's kind of weird, right? But it solves a whole bunch of problems. No longer have to deal with any sort of OR mapping issues, right? Which have always been problematic. It actually works on top of SQL and NoSQL databases, and it lets you publish events in a very reliable fashion. And you basically get this eventually consistent mechanism. So it's kind of cool, but different. But then the other complication is that the event store only supports primary key-based lookup of entities. So if you want to do effectively joins, you end up having to maintain separate views of the data and writing code that denormalizes the stream of, you get a stream of events coming in and it updates these denormalized view of the data that you can then query to support the UI. So for example, in the app I'm working on, I got text search. I want to do text search, and so I'm using AWS Cloud Search. So that's my view, and I have a service that's subscribing to entity change event that's then triggering the indexing of the document. And then I have another service that's running text queries against Cloud Search to support the REST API that's communicating back to the JavaScript client. So anyway, so that's kind of, it's a real interesting approach, and I'm sort of hoping to actually open source a big chunk of this because I think it's useful.
Do you have fault tolerance? Kind of what happens if pieces of this thing go down and then you're losing events? So have you replicate them somehow, or do you have multiple?
Well, that's a really good question. So the event store, so you're assuming that the event store is fault tolerant, right? So then if a consumer, so basically the consumer is sort of like a persistent subscription. So like if it was AMQP, it would actually be the kind of the model is you've got this named persistent queue that just like queues up the events until the consumer can consume them. So you could take a service offline for a day, and then when it came, like if you took off the text search indexer offline, then when it reconnected, the system would say, well, I've got, here's 1,000 events for you to index, and it would just blast them at it. So, and then, you know, so it sort of kind of works quite well. Services can kind of come up, go down, and because it's all message-based, nothing gets lost.
So how do you deal with the ever-growing list of events?
Disk is cheap.
Right, but if you have 1 billion events to process, wouldn't that take a long time?
Well, I guess the assumption is that you wouldn't be down long enough to...
No, but it's not just about being down, right? Because you always start, in your example, you had a new account, and you read the
yeah. Oh, there's a ton of details. So you're right. So I mean, the handy analogy is like, if it was a bank account, you would see a stream, you'd see an open account event, and then you'd see a series of debits and credits, right? And I guess what you're saying is after n years, that's a mighty long list of events. So the solution is actually to periodically to take a snapshot of the current state of the entity and basically insert that into the event stream as a snapshot event.
I like it.
So that you then only have to go back as far as the most recent snapshot event and then load that and then replay forward. And, you know, so it's just like every n events, every, you know, whatever makes sense to optimize it.
You have to lock the row. You have to lock that object to do this, right?
Well, the scheme I have right now is actually optimistic locking. So when you load an entity, it's at version n, and then when you call update to append new events on, you just make sure that it's still at version n, and throw a optimistic lock exception if it's not, and then you can sort of retry that transaction.
You can also look at how Bigtable handles the SS tables and compactifies them on the fly. You don't have to lock it.
Yeah, I mean under the implementation, it's this is implemented using ACA actors, and so it's sort of I mean, there's no sort of real locking other than some serialization around based on the actor queues.
The question is, when you take a snapshot, right, you assume that thing will be in a consistent state, right? Then you take a snapshot. Otherwise, let's say even because you are event stream, right, event could be out of order. How you know there's a state you can take a consistent snapshot?
The event for an entity must always be in order. So if the whole model is load an entity at version n, generate some more events, you try and append those events, that will be you have to check that it's still at version n, right? Then so you're guaranteed that at that point there's a linear event stream.
Does that mean that these events are coming from a single service? Because you have to serialize somehow, right?
Well, the actual updating, so the events for a given entity are being generated by whatever service is handling the request, right? And so by virtue of implementing an optimistic locking check, you could actually have multiple services still trying to update the same entity concurrently, but because there's an optimistic locking check, they're effectively being it's being serialized at that point.
And who's going to deal with the optimistic conflict when there's a conflict?
Well, it gets bounced back to the service.
So does that mean that the events are published sequentially?
Well, this is not really the publishing side. This is the kind of, yeah, this is the generation side. So then, I mean, there are interesting issues in a system where, on the consumption side, where the order is kind of, it's not arbitrary. I mean, there's a certain non-determinism about the ordering. But kind of with respect to a particular entity, it should all be sensible.
It's also because there are some issues like, let's say, service crashes, right? There is some queue of events, you spin up a new, it has to read, but maybe some of the events haven't been processed by some other service, so you read back inconsistent. In other words, to get, let's say, some value like credit limit, you have to read source of truth, but let's say source of truth hasn't processed some of events of updates yet. So you will read something without this delta of events, and then what, you're like start issuing new orders.
Yeah, well, it's kind of, could the order management, I mean, the customer management service, could it really go down? Having problems putting this into words, but it's hard to imagine the credit limit scenario getting out of whack. Because it's kind of like if the customer management service has committed that event, the event store has accepted it, and assuming the event store has a highly available architecture, any consumer will get that event.
Unless it crashed.
Oh, unless the event store crashed and you're effectively sort of dead in the water at that point. But you know, if the event store comes back up, then it will have done its recovery and got, you know, the state of the world will be correct, and then any connected clients will see that. Yeah.
Sorry, is there a single event store, or is there an event store for every table that you have?
There's basically a single event, a single event store. So all of the services are talking to it.
So how is that different from having a single database?
Well, actually, that's an interesting question. So well, there's sort of two answers to that. So one approach is that a given entity type, say order, is only accessible, should only be accessed by the order management service, right? And anyone else should just be subscribing to events that are coming out of the order management service, and then they're maintaining their copies. So effectively, it's, even though there's one piece of infrastructure, it's logically divided up by, you know, stuff that service A owns, stuff that service B owns. So that's sort of one answer to that. Now, interestingly, in theory, different services could actually access the same entity. But because everything is in terms of events as opposed to a database schema, which is a lot more complex, I sort of would argue that things are still kind of loosely coupled, right? Like still services are only communicating in terms of events as opposed to some internal, possibly complex database schema.
So could you not just put an abstraction layer above the database then?
You could, but yeah, but then I mean, yeah, but what is that? What's an abstraction layer though, in that context? Okay, so it's kind of interesting issues. So I guess I got handful of slides, and I was just going to like quickly talk about the system that I've implemented, just to kind of give some concrete examples. So, like for instance, I've mentioned this already. I have an API gateway that's written in Node.js, and maybe if I was motivated, I'd go replace it with some event-driven JVM framework. But yeah, it seems to be working fine. Kind of have a love-hate relationship with Node. As in, like, I hate JavaScript, but Node is useful. So my main services are actually built using Spring, Scala, and then the overall framework is actually Spring Boot, which is an incredibly cool technology for building microservices, because it, like, you kind of just have to write a minimal amount of configuration, and Spring Boot provides this convention over configuration mechanism that just figures out the rest of your configuration and gives you a running app. And it really is quite remarkable. Plus, it's got Maven and Gradle plugins that package your app as a self-contained executable jar file. So it actually embeds Tomcat or Jetty inside the jar file. So to run one of these microservices, it's just java-jar foo.jar, and it just like starts up. So you don't have to worry about properly configuring Tomcat or anything like that. So that's huge. And then it gives you a whole bunch of production features like health check. So you just include one dependency like Spring Boot actuator, and you get a /health URL that like tells you the health of your system. And the health checks, like if you've got MongoDB in there, the health check just knows that there's MongoDB as part of the system, and it will give you health information about the MongoDB connection. And this is just without you having to do anything. Plus, you've got a really nice way of externalizing the configuration. So you can just set environment variables to specify like the database host and port and user credentials. And that's really cool because that works well with Docker containers, because the way you configure those is docker run -e some environment variable, and so it just kind of works. So very excited about that. And as I mentioned, got an event-driven architecture that's using event sourcing, and then some of the denormalized read-time views are using DynamoDB. Actually, the event store is sitting on top of DynamoDB. Some of the views use DynamoDB, but then I'm also processing the event stream and updating Cloud Search, AWS text search mechanism. So that kind of works. And then I have a Jenkins-based deployment pipeline, one per microservice, that ultimately spits out a tested Docker image at the end of it. So each app is, even though it's sort of a jar file, it's a nice packaging mechanism. The fact that regardless of whether it's the API gateway or one of the Java backend services, at the end of the build pipeline, I get this Docker container that you can just run, and it doesn't matter what's inside it. And of course, the analogous thing, say with Netflix, is they build AMIs. But if anyone's built an AMI, you know that that takes several minutes, right? Whereas with Docker, I can build a Java application container in, I think it was 6 seconds, 6.4 seconds. And then it takes 38 seconds to actually push that container into a repository, into a registry on S3. And then you can imagine it's another 30 seconds to pull it down into the production environment and launch it. Just like frickin' cool, really. It really is. Super lightweight, super agile. And then one of the other steps in the build process, it actually builds the Docker image and then just fires it up and pings the health URL just to make sure that it's kind of working. So that's kind of nice.
So how do you deal with like already running services? So let's say it's a production environment, you build new version, you deployed it, but there are still older version running and possibly handling requests, you need to take those down, right? And
yeah. Well, the whole deployment mechanism is kind of hacked together right now. So basically, I have a Python script that actually looks in Jenkins, sees what the latest version that's come out of the deployment pipeline is, then actually logs into my one production server, because my app's web scale, and sees what versions are running, and then generates a shell script that says, download the new, well, does a Docker pull of the new version, a Docker stop an RM of the old version, and then a Docker run of the new version. And it just does that for any services that need to be updated.
Well, I mean, if you stop it means like it could be handling requests in the middle, right? So you kill potentially some.
Yeah.
Or many, possibly.
Yeah. Well, not many users right now. Actually, you know, it's kind of funny. The user's either deploying new versions or using the system. So, no, I mean, basically going forward, I could imagine having multiple EC2 instances, and then I'm actually thinking of looking at Mesos and Marathon to do the deployment, and then there could actually be side-by-side deployments of old and new versions, and that should all work just fine. But the nice thing is sort of like, I think, right, you know, instead of having to run 8 EC2 instances, I've just got like one EC2 instance. You know, one day there will be 2 EC2 instances, and a bunch of Docker containers running inside each one. And so it's, you know, very, much more cost effective, and also much more agile, because as I mentioned, you know, it's so fast to build and push and pull these Docker containers. So anyway, talked about a whole bunch of stuff for a really long time, so that's my talk. If you can remember at the beginning, I said monolithic apps, you know, they're simple to develop, deploy, but it's, you know, once they get to a certain level of complexity, you kind of run into problems. So the solution is to apply the scale cube and functionally decompose the app into what are now called microservices. So you end up with an architecture that looks like this. And, you know, if you're wondering, well, I'm working on a monolith, what am I going to do? Like, well, you know, tomorrow morning you could go into the office and start incrementally extracting services out of your monolith, write a glue layer to actually connect your nice, simple new service back into your hideous monolith, and you go through that enough times and you've incrementally refactored to a microservice architecture. Best of luck. So anyway, you know, here's some contact info. You know, if you have any questions, you know, connect with me on Twitter or shoot me an email. And then, you know, one of the websites I created is actually microservices.io, which is, the goal of that is to be a collection of patterns for this microservice architecture. So right now there's 3 patterns: monolith, microservice, and API gateway. And at my current rate of progress, sometime early next year, there should be a 4th pattern. So I wrote the first 2 back in May and just published the 3rd one like last week. I need to pick up the pace there. And then also plainoldobjects.com is my blog, and there's a bunch of links to presentations which are on SlideShare, and sort of, you know, presentations and articles and blog posts on microservices and other sort of related topics. So hope you found it useful. Thanks.
Thank you.